Okay, welcome to lesson 1.5, properties of limits. To get started today, we're going to finish up the last example from yesterday. We're looking at a true and false question. We've got a couple statements here. So the first one says the limit of f at x as x approaches a may exist even if f at a doesn't equal the limit, or even if f at a does not exist. So this statement, hopefully you figured out, is a true statement. And how do I know? Well, this first one here, where there was a value for f at a, but it's not the same as the limit, that's the same as example 2 from lesson 1.4. And then the second part here that says, okay, the limit can exist even if the value doesn't exist at all, that's the same as example 3, part D. That was the one with the hole, right? All right, so part B. So here we've got, if the limit from the left is equal to the right-hand limit, so the left-hand limit is equal to L, which is equal to the right-hand limit, then the limit of the whole function is also equal to L. And this is actually just the definition. Hopefully you found that makes sense, and the statement, of course, then is true if it is the definition. So the next part here says, if the limit of f at x as x approaches a is the number L, then the value of the function, the y value of the function at a, must also be equal to L. So this might be true, like it was in example 3, part A, but might not be true. And that is like example 3, part D, like we just saw above. So because it might not be true, we have to say that this statement overall is false. It's not always true that if that's the limit, then the value of the function is also L. All right, the last one in part D, if the limit of the function as x approaches a is equal to f at a, then the graph of f at x, that should say an x, will flow through the point a comma f at a. So okay, maybe we need to think about this again. So if the limit exists and it's the same as the value of the point, then the graph will flow through the point. So what we've got here is, if I've got a function, so let's say this is a picture of my function, and this is my a value, and then this is my f at a. So they're saying if the limit, so the limit here as I approach x, as x approaches the value of a, is going to be equal to this number f at a. Well, if they're saying that's also the value of the function, so that means I can actually color in that circle, right? And so that means that, again, if I were to trace this function, I would flow through that point. So this is true. All right, so starting today's lesson, we're going to be looking at the properties of limits. So what we're talking about here are, like, what are the rules? How am I allowed to manipulate limits? So for example, here are some common rules that people like to make up or break in math. The square root of a plus b is not equal to the square root of a plus the square root of b, right? That's a rule for us. So we're saying you can't do this. Also, thinking about the sine of 2 times theta, that's not the same as bringing the 2 out front and saying 2 times sine of theta, right? This one here would be a horizontal compression, and this one here would be a vertical stretch, a change in amplitude or a change in period. These are not the same thing. So what we want to know is what is and what isn't allowed when limits are involved. So we've got 7 properties we're going to go through here. So the first one said, for all of these, we are looking at a is just some real number, and f and g both have limits that exist at x equals a. So we're going to make that assumption for all of these examples. So if f is a polynomial function, so first looking just at polynomials, so it could be linear or quadratic or cubic, something like that. Well, then we know that the limit as as x approaches a is actually going to be equal to the value of the function. And that's because we know that there's no discontinuities for a polynomial. And we know that the domain is the set of real numbers, right? So in our example here, we've got the limit as x approaches 3 of this polynomial. It's just a quadratic. And what that tells me is I can actually just plug 3 into the equation. And we've been doing this, right? We did this yesterday. But here it is, as a rule, you are allowed to do this to find the limit. All right, the second rule, the limit of a constant is equal to the constant. So this is saying if you take the limit of some number k, right, we're saying k is some real number, as x approaches a, you're just going to get the answer k. This makes sense because this is really just a horizontal line, right? This is my f at x. So it's a horizontal line with no holes. So here, the limit as x approaches -1 of the function y equals 5 is just 5. This is kind of an extension of the polynomial function. This is your most basic polynomial function. So what I'm looking at in this example here is the graph that goes through at 5, right? This is the graph that I'm looking at. And so, of course, as I approach the x value of -1, the y value of the function does approach 5. All right, the next one, the limit of x as x approaches a is equal to a. So now what we're looking at is the function f at x equals x. Again, this is just a special case of number 1 as well. This is just a diagonal line, y equals x. And so this makes sense as well, that when x approaches -1, to find the y value, I can just plug -1 into the function. In this case, it's a special case, right? Because there's no calculations to do at all. All right, number 4, the limit of a sum is equal to the sum of the limits. So here I'm taking the limit of an addition, and we're saying that's the same as taking the limit of the first thing, the limit of the second thing, and then adding those two answers together. So it doesn't matter what order I do. Remember that up here in my example for radicals, that's not true. You can't, here if I'm taking the square root of the sum, that is not the same as the sum of the two radicals. So that's against the rules for radicals, but it's okay for limits. So here in my example, I've got the limit as x approaches 2 of this sum. That's going to be the same as taking the limit of the first thing and adding the limit of the second thing. Now we saw above that I can take the limit of this polynomial function just by plugging 2 in. And then we're going to see, actually, I'm kind of skipping ahead here. This is rule number 6. I can take the limit of this thing just by plugging 2 into this. And then, of course, I can figure out that this is 12 plus a half, so 12.5. All right, number 5, the limit of a constant times a function is equal to a constant times the limit of a function. I just want to talk, number 4 here, I was using the sum, but it would work the same for a difference. So if it was a subtraction, it'll work the same. So back to number 5. Here we're talking about if I have a constant or like a coefficient in front of a function, I can pull that coefficient outside of the limit. So we know that this is not the case. Remember, we just looked at for trigonometry, right? That's not the case. You can't just pull that constant out front, but it does work for limits. So in my example here, I've got the limit as x approaches 3 of 10 times this line. So that tells me that's the same as 10 times the limit. And so you can see how sometimes this would be convenient to be able to calculate this on its own and then multiply the answer by 10 at the end. So here now I can just plug 3 in and take the limit. And then I can multiply those answers, so 10 times 7. Sorry, I added when I plugged in there before. So it's 3 plus 2, and then it's 5 times 10 is 50. Okay. All right. The limit of a product or a quotient is equal to the product or quotient of the limits. So for a product, I can just say that if I'm taking the limit of a product of two functions, that's the same as taking the limit separately and then multiplying those two answers. For a quotient, there's one other thing that you need to think about because we're talking then about dividing. So whatever I'm dividing by can't equal 0, right? Then that won't work for me. So here in our example, we are looking at the limit of a quotient. So we're saying that's the same then as taking the limit of the numerator and dividing by the limit of the denominator. And again, sometimes this will be more convenient than others. But what it does allow me to do, and what I did up here is I did that without actually rewriting it. I took the limit of the constant 1, and I got the answer 1, and I took the limit of the denominator x, and I got the answer 2. Right? So I'm just using that rule much more quickly by not writing out this step. So here now I can plug 0 in. And as you've seen, again, we don't always write this step out. We sometimes just go to plugging the 0 right in. All right. And typically you shouldn't work across the page like this. You should work down always the page, but I'm running out of space. All right. The limit of a power. And remember, a root is just a special type of power, right? It's like a fractional power is equal to the power of the limit. So again, this is nice to know. If I'm taking the limit, and here I'm taking the limit of this whole thing, right? That's the same as taking the limit first and then raising it to the power on the outside. So again, for our example, we've got the root instead. So instead of taking the limit of the root, I can take the root of the limit. And it's just handy to be able to move these things around so that I can do sometimes an easier calculation. And so a lot of times as well, you'll see that we know that we can plug the 2 in here, so we go right to this step of taking the limit without actually showing that this is really what we were doing in our heads. And so I get the square root of 2 times 2 plus 5, which is the square root of 9, which is 3. All right, I'm going to pause the video here so it's not too much to upload, and we'll continue in the next section.